Hello everyone. Today we are going to discuss an important graph algorithm, that is topological sorting. What is topological sorting? Topological sorting for directed acyclic graph is a linear ordering of vertices such that for every directed edge uv, the vertex u comes before vertex v, okay, in the ordering. So first of all, topological sort can only be done on directed acyclic graph. Okay, if the graph is undirected, if the graph has a cycle on it, we cannot do a topological sorting. And what we have to do is, in a directed graph, there are different vertices, and if we have a direction in edges, we have to do a ordering of the vertices in the way that if there are two vertices where there is an edge bit from A to B or from U to V, U has to come before V in the ordering. So let's give you an practical example. Before you go to office or school, uh, look at this graph. This graph is explaining your dressing ordering, right? How do you dress? Now you see we have different dress like components in the graph, and there should be an ordering, so you cannot just put on your jacket at the beginning, right? There must be an ordering. Of course you have to wear your shirt before your jacket, right? And also you cannot just put on your tie at the beginning, because you have to first put on your shirt, right? So you see here that there some ordering has to be followed, and after making dependencies on the uh, different dresses, then you can create a directed graph, and based on that you can make some kind of ordering. Suppose here, look at this one, we can just put on our shirt first, right? We can say we can put on our shirt first and then tie next, right? And then we can put on your say we cannot still put on our jacket, right? Because jacket is still dependent on the belt. So we can then put on our underwear and then say 3, right? And then we put on our pant 4, then put on our socks and then shoes, right? And then I can in the 7th I can put on my belt and finally jacket, right? Okay. So this is one ordering, how I want to dress. And not necessarily I have to start with the shirt. I can also start from my socks or underwear, right? But the thing is, this is one solution uh, of how I can dress. And the ordering, the output ordering is, we can call it that this ordering is the actual result of a topological sort. That means sorting the elements of the graph in such a way so that the dependencies are maintained. Okay. Now, one thing is the topological sorting for a graph is not possible if the graph is not direct acyclic graph. So first of all, if this is an undirected graph, there is no dependency, right, between the vertices. So undirected graphs are ruled out. And then if there is a cycle, obviously I cannot make any ordering. Let's just look at this graph. You see that D, right? Thing like this. B is dependent on D, right? B is dependent on D. But the D is also dependent on B. So you see D is dependent on E is dependent on C is dependent on B, right? So if you want to do an ordering, if you do like B and D like this, put B first and D last, that's not possible because you B cannot come before D, right? The reason is B is dependent on D. And if I say, okay, then let's put D before B, that's not also possible, because you see here that if I want to put D before B, then I have to put E before D. I have to put C before E. Now you see C and B cannot be after C, right? So it's a kind of like D is dependent on B is also dependent on uh, D is also dependent on B is dependent on D. So if there is a cycle, there is no topological ordering. So just think like this. If something was like this, if your dress one, you had to put dress one before dress two, right? And if there was a dependency like you have to put dress two before dress one, then you could not even dress, right? Because they were dependent on each other. Okay. So from here, now you understand if I have a directed acyclic graph, a directed graph, how do I start my topological ordering? So one thing to notice here is I have to start somewhere which is not dependent on anything, right? Okay, so here is where in degree of vertex or node comes handy. So in degree means the number of dependencies or the number of degrees that a node has. So here, suppose for T, the in degree is how much is the in degree? Like how many uh, components it is dependent on. In degree is 1, right? What about shoes? Shoe is dependent on 3 components, right? In degree is 3. Socks, they are not dependent on anything, right? Shirt is not dependent on anything. Under is not dependent on anything. Pants is dependent on one component, right? So can we say that if we can calculate the in degree of the vertices, we can start with the in degree which has a 0. So we can either start with shirt, we can start with socks, we can start with shorts or underwear, right? Can we do that? And after we do that, you see that what happens is after I am done, suppose I have done with shirt. So I can say that, okay, shirt is done. So I am done with shirt, right? So can we say that now, since shirt is done, so these dependencies are also gone, right? So instead of now tie has a dependency, tie will have a dependency of 0. So the in degree for tie becomes 0 now. And in degree for belt was previously 2, now is 2 minus 1 equals to 1, right? Okay, so this is an important thing to do topological sorting. So let's go to our algorithm. There is very easy to understand algorithm. From the definition, the topological sort may look a little bit scary, but the algorithm is easy. So we have to have a map uh, which actually calculates the in degree, which stores the in degree of each vertex. And then there is a queue where we will just put the vertices that has an in degree of 0, because we can just process those ones that has an in degree of 0, right? And then this is the ordering or result. This is the result. So, okay. And this is actually a variation of BFS. So what we're going to do is from this queue, uh, everything that is in this queue can be processed because they don't have any dependency, right? So repeat until the queue is empty. We will dequeue a vertex from the queue, add it to our result ordering, and decrease the in degree of all vertices neighboring all the V's neighbors by 1 in the in degree map. And then if another vertex becomes has an in degree of 0, we'll add that to the queue. And finally, we'll see if all the vertices have been processed, right? In that case, we can say that, okay, topological ordering was successful. Otherwise, there was a cycle. So let's look at it one example. Look at this example. So here we have a graph, right? Now let's calculate the in degree of the graph. So, and we'll put them in the map, right? Okay, so map says uh, this one stores the in degree of each vertex. So you see the in degree of B is, what is the in degree of B? is 0, right? It's not dependent on anything. In degree of A is also 0. C is dependent on one another vertex. So C in degree, like what is the edge number of edges in incoming edges? In degree is the number of incoming edges. So number of incoming edges for C is 1, for E it is 2, for F it is 2, sorry, for D it's 2, right? Okay. Then in the Q, we can put all the vertices with in degree of 0. So how many vertices we have like that? We have 2 vertices, A and B, right? And ordering, initially we haven't start processing anything. So the ordering is, our ordering is empty. And let's see how many vertices we have. We have like 3 and 6 vertices, right? Okay. So eventually, after processing everything, if my ordering has like 6 vertices, then I can say, oh, okay, we are successful in ordering or doing topological sort on this graph. Otherwise, it's failed. Probably there was some cycle somewhere, right? Okay. So what we have to do is the algorithm says dequeue the first vertex V from the queue. Okay, so we have to dequeue it and add it to the result. That means we have processed it, and immediately we just reduce the in degree of all neighboring vertices for that vertex. And if any other vertex now has an in degree of 0, updated in degree of 0, we have put it in the queue. Okay, so let's go to the second step. So you see that, okay, so we dequeued B. So we dequeued B, and then the neighbors of B were like C and D, right? So we reduce the in degree of C and D by 1. Okay, now C's new in degree becomes 0. So we add C to the queue, right? And we had dequeued B, so we had put B to the result or the ordering. Okay. Next, we are going to dequeue C, right? No, sorry. Yeah. Next, we are going to dequeue A. Yeah. So basically, Q is first in, first out. So probably it would have been better if we could just write like this. Instead of like this, I could just put, say, C is added here and A was here, right? Okay. Okay, so next we are going to dequeue A, right? Okay. Okay, another thing, like it doesn't matter if I dequeue A or C first, it's up to you, okay? Because it's the same thing. So next we are going to dequeue A. So we dequeued A, put it into the ordering, right? And A has a neighbor D, so we reduce the in degree of D, and now the new in degree becomes 0, so we add D to the queue. Okay. Okay. Next, we dequeue C. We dequeue C, put it into the ordering. C had 2 neighbors, F and E. We reduce their in degree by 1. And now you see there is no new vertex with in degree of 0, so nothing is added to the queue. Okay, so next, we dequeue D, put it into the ordering. Now you see D had 2 neighbors, E and F. We reduce the in degree of E and F by 1. Okay. And both E and F now has in degree of 0. So we add both of them into the queue. Okay. Next we dequeue E. Well, E doesn't have any neighbor, right? So there is no need to decrease the in degree for any other vertex. And finally, we dequeue F. F didn't have any neighbor. So yeah, so F didn't have any neighbor, and we just added E and F to the ordering. And finally, we see that we have like 6 vertices here. So that means we're successful in doing a topological sort for this graph, right? Okay, so if we had like if our queue was already empty and after counting we could see just five, we could say, oh, okay, I had to have like six vertices, but I got five. That means there must be a cycle. Because of that, the queue got empty, but all the vertices were not added to the result ordering. So what is the runtime of this algorithm? So at the beginning, you see that we are creating a map for each vertex, right? About the in degree. So there are like V vertices in total. Uh, so once we are actually creating an in degree map, uh, we have this is an order of V operation, right? For V vertices, we count how many incoming edges each vertex has. And then we initialize a queue. This is a constant time. Uh, okay. Uh, and then uh, we initialize an ordering, that is fine. And then we run a for loop, repeat until queue, or run a while loop until the queue is empty. So how many times we can dequeue from the queue? At most V times, right? So this is an order V operation. We dequeue from the queue every time. That's an order of one operation. Decrease the in degree of all vertices. Uh, yeah. So we decrease the in degree of all vertices that are neighboring to V, right? V is the one that is just dequeued. So you see that how many neighbors in total we have. Like if we had like E edges, right, in the graph, that means over the course of this while loop, we are going to visit like um, not E vertices, because there are E edges. E edges means there are E neighbors. So that means E times we are going to decrease the in degree of other vertices, right? So this whole thing becomes order of E. Okay. So if we add them all together, it's order of V plus order of E. Okay. So it says like if the graph is sparse means there are not many edges. In that case, we can just say for a sparse graph, we can say that the number of edges are not many. So we can just say order of V plus E is like kind of order of V. Another question for you, what about a dense graph? For a dense graph, E is almost, say, in the worst case, it can be order of V square, right? Do you remember that? So that's a different thing. But if it's a sparse graph, then it's going to be pretty fast. Okay, so that's about topological ordering. And to better understand this, I would suggest you to look at one of the problems with topological sorting, where we'll actually code it and it will be more clear to you. But I hope, although this is a very interesting algorithm, although this algorithm at the beginning looked a little bit scary, uh, that but the solution actually is really easy. One last thing, what is the application of topological ordering? Uh, so one good application for this is, say, when you are taking course in your undergrad or grad, right? There is something called prerequisite. So say you want to take algebra 2, right? But before you take the algebra 2, uh, you have to take like algebra 1, right? So there is a prerequisite. And also say if you want to take something else, say uh, I don't know, calculus 1 or something. It might be the case that algebra 2 is a prerequisite to calculus 1, right? Or any other case. Suppose you want to take CS 0111. Algebra 2 might be a prerequisite to this. That means you have to follow a prerequisite to take the courses, right? Every semester you have to plan that, okay, this semester I have to take algebra 1 because next semester I want to take algebra 2. And in the third semester I'm going to take like CS or something, So I have to plan beforehand. Otherwise, I cannot just say take CS 101 at the beginning and then algebra 1 later, right? So this is one application of topological ordering, like course scheduling or course planning, how I want to take courses. The other thing is when you are actually running programs or compiling programs, you see that there is a lot of dependencies. You are using different libraries, right? And those things get compiled first, and then your program gets compiled. So if there is a cycle in dependency among the components of your program is not going to compile because A will depend on B, B will depend on A. So there is a deadlock there. So that's another example of topological sorting. So hopefully that helps. We'll see you again with another algorithm or another problem. Since then, bye.